Welcome back to the deep dive. We're ready to get into the details and pull out the key insights from some fascinating material for you.
Yeah, and today we're looking at something really intriguing, how these tiny, tiny signals, ones you literally can't feel, might actually change how we learn to walk and adapt.
Okay, so this deep dive comes mainly from a really accessible breakdown we found on the Oriems Fit Research Digest blog. It simplifies a study, a research paper from Harvard Medical School and University College Dublin.
That paper was published back in July 2023 in iScience. So, a solid scientific source behind the blog post.
Absolutely.
Yep.
So our mission here is to unpack that science. What was the experiment? What were the maybe surprising results? And, why does it even matter for movement or maybe even recovery?
Let's get into it. The central concept is subsensory electrical stimulation.
Subsensory. Okay, break that down. Below sensory.
Exactly. You know how some electrical stimulation, like from a 10S machine or maybe an EMS device, you feel it buzzing or tingling, maybe even making muscles twitch?
Yeah, definitely feel those.
Right. Subsensory stimulation is electrical current that's applied, but the intensity is so low it's below your normal sensory threshold. You just don't consciously perceive it on your skin.
Electricity you can't feel. Why would that do anything? Seems counterintuitive.
It does, doesn't it? But there's this idea from signal processing. It's called stochastic resonance. Bit of a mouthful, but the basic concept in biology is that sometimes adding a tiny bit of random noise,
Noise. Like static.
kind of, yeah, like a controlled randomness, adding just the right amount of this noise can actually make a biological system, like our nervous system, better at detecting really weak signals it might otherwise miss.
Okay, wait. So like adding a faint background hum might actually help you pick out a super quiet whisper across the room.
That's a surprisingly good analogy, actually. The theory here is that these tiny electrical signals could act like that helpful noise, potentially boosting our ability to sense very subtle information coming from our own body.
And that body sense, proprioception, that's key for walking, right? Knowing where your limbs are.
Absolutely critical. Proprioception is your brain's awareness of your joint positions, muscle stretch, how things are moving. You need it for balance, coordination, and especially for adapting when things change, like hitting uneven ground or, like in this study, dealing with an outside force. So the big question was, could these subsensory signals tweak proprioception and help us adapt our movements?
And the researchers involved, you mentioned Harvard, University College Dublin. The source also lists Spaulding Rehab Hospital, the WIS Institute. That's some serious brain power.
Definitely. A top-tier collaboration. It suggests this isn't just a fringe idea. It's something established researchers are seriously investigating.
All right, so how do they put it to the test? The study had, 30 healthy adults? Youngish, 20s and 30s?
That's right. And they used a pretty cool piece of kit called a locomat. Think of it as a robotic exoskeleton for your legs hooked up to a treadmill. It's often used in rehab.
So the robot can, influence how you walk?
Precisely. The researchers programmed it to create a specific challenge. While the participants were walking, the robot applied a controlled force to their right leg, but only during the swing phase, when the leg lifts and swings forward.
Okay, and what did the force do?
It was designed to push the leg a bit further forward than normal, basically increasing the step length on that side.
Creating a controlled disruption, a perturbation, they call it.
Exactly. It throws off your normal symmetrical walk. And the body naturally tries to fight back, to adapt its muscle patterns, to get back to that comfortable, even stride, even with the robot pushing.
And while that adaptation battle was going on, that's when they applied the subsensory stimulation.
Yes. They put electrodes on the skin over the hamstring muscles of that same right leg, the one getting pushed by the robot.
Hamstrings, okay.
Yeah.
And the stimulation itself.
It was what's called Gaussian white noise, basically. Random electrical fluctuations, but very low amplitude. And here's the crucial part. They tuned the intensity for each person individually, setting it at 90% of their sensory threshold.
So just low enough that they couldn't feel it.
Just below that point. The idea was to target receptors inside the muscle, like muscle spindles, not the touch receptors on the skin surface.
Right, so electrodes on the hammy, undetectable random current, robot messing with the step. What did they compare? What were the conditions?
Okay, so people came in on separate days to avoid fatigue effects. They did two main types of 10-minute walking sessions, and the order was randomized so it didn't bias the results.
Great sense.
Condition one was the stim condition. Subsensory stimulation was on continuously for the whole 10 minutes while the robot was applying that force.
Okay, constant stimulation during the challenge.
Condition 2 was the nostim condition. This was the control. The stimulation was turned on only for the first 20 seconds, just to make sure putting the electrodes on wasn't the effect. Then it was switched off. But the robot force continued for the full 10 minutes.
Ah, okay. So they could compare adapting with a continuous signal versus adapting basically without it.
Exactly. And the main thing they measured was how that right step length changed over time. How fast did they adapt and how much did they adapt? They tracked it while the force was on and then also looked at how quickly they went back to normal walking when the force suddenly stopped.
Okay, the moment of truth.
Yeah,
What happened? You said it was surprising.
it really was in some ways. The big takeaway. Yes, this subsensory stimulation definitely significantly changed how people adapted their walking pattern.
Faster or slower?
Faster. In the stim condition, with the continuous stimulation, participants adapted much more quickly. On average, it took them about 11 steps to adjust to the robot's push.
11 steps. Okay, and without the stimulation.
In the nostim condition, it took them closer to 20 steps, 20.1 on average. So the stimulation cut the adaptation time almost in half, a 45% speed up.
Wow. Nearly twice as fast, just from something you can't even feel. That sounds amazing, like a clear win for stimulation.
You'd think so, wouldn't you? But here's the twist, the counterintuitive part. Although they adapted faster with stimulation, the adaptation wasn't quite as complete.
Less complete. What does that mean?
It means that by the end of the period where the robot was pushing them, the stim group hadn't quite gotten their step length all the way back to normal. Their affected step length was still about 9.4% longer than their baseline symmetrical step length.
Okay, so 109.4% of normal. And the other group, the slower ones.
The nostim group, who adapted slower, actually got closer to their original pattern. They ended up at about 103.9% of their baseline step length.
Huh. So faster adaptation with stimulation, but they didn't fully correct the error. Slower adaptation without it, but they got closer to the original goal.
Precisely. It's this really interesting trade-off between the speed of adaptation and the, let's say, accuracy or completeness of it, at least within that time frame.
Fascinating. Was there anything else significant in the results?
Yeah, a couple other things. They looked at de-adaptation, too, how quickly people went back to normal walking once the robot force stopped. And again, the stim group was faster.
Faster de-adaptation, too.
Yep. Took them about 12.6 steps versus 21.1 steps for the nostim group. It suggests that whatever the stimulation was doing, its effects also washed out more quickly once it was gone.
And you mentioned something about the order they did the sessions. Stim first versus nostim first?
Right. That seemed to matter. The effects that faster but less complete adaptation were actually stronger, more pronounced when people did the stim condition first.
Interesting. Why would that be?
The researchers suggest it might have something to do with, like, motor learning novelty or how the brain first encodes and then recalls these adaptation patterns. Maybe experiencing the stimulation during the initial exposure to the task had a bigger impact. Still needs more research, though.
Okay. And what about differences between people? Did everyone react the same way?
Oh, definitely not. This was another key finding. The stim condition caused significantly more variability between different participants. So the effect size varied a lot from person to person.
More intersubject variability.
Exactly. But importantly, it didn't increase variability within a single person's steps. Their step-to-step consistency while walking was about the same in both conditions. The stimulation didn't make individuals walk more erratically, it just made different people respond differently to the stimulation.
Okay, let's recap the findings. Faster adaptation, but less complete correction. Faster de-adaptation. Session order mattered. And much more variation between individuals with the stimulation. That's quite a mix. How did the researchers try to explain all this, especially the faster but less complete part?
Yeah, that definitely needed a more complex explanation than just stimulation enhances sensitivity. They really zoomed in on those muscle spindles we mentioned earlier, the tiny sensors inside the muscles.
Remind me quickly, what do they sense again?
They're key for proprioception. They detect two main things: how much the muscle is stretched, and crucially, the rate or speed at which it's stretching. They send this info back to the nervous system through different nerve pathways, mainly called IA and type 2 afferents.
IA for rate, type 2 for amount of stretch.
Broadly speaking, yes. IA fibers are very sensitive to dynamic changes, the speed of stretch. Type 2 fibers are better at signaling the static length or position of the muscle.
Got it. So how could the faint electrical signals mess with these?
The main hypothesis is something called partial depolarization. The idea is the electrical current makes the nerve endings of the spindles a bit more excitable, closer to their firing threshold.
So they might fire more easily or more often for the same stretch.
Exactly. And this increased excitability could lead to that weird combination of effects. This is where they proposed a dual effect hypothesis, looking at those IA and type 2 fibers differently.
Okay, dual effect. How does that work?
Well, the theory goes like this. The increased sensitivity in the IA fibers, the rate detectors, might make the brain perceive that sudden push from the robot, that rapid stretch, more strongly or maybe even slightly earlier.
A faster uh-oh, something changed signal.
Kind of, yeah. And that heightened, quicker perception of the change could trigger the corrective motor commands faster, like activating the hamstrings sooner to counteract the forward push. That would explain the faster adaptation speed.
Okay, makes sense.
Yeah.
IA speeds things up. So where does the less complete part come from? That must be the type 2 fibers.
That's the thinking. The altered signaling from the type 2 fibers, the static link detectors, might subtly change the brain's internal sense of where the muscle should be, its target length during that phase of walking.
Changing the goalpost, basically.
A little bit, yeah. This altered target signal could then lead to the hamstring activity, which helps slow the leg down, being inhibited or switched off slightly earlier than it normally would during the adaptation process. If you start braking too soon, you don't quite get back to the original step length.
Wow, okay, that's intricate. So stimulation gives a faster heads up to react because of the rate sensors, IA, but it also slightly shifts the perceived target because of the length sensors, type 2. So the question isn't perfect.
That's a really good summary of the hypothesis. It elegantly ties together the different spindle functions with the observed results.
And what about the high variability between people? Why such different responses?
The researchers suggest a few possibilities. Simple anatomical differences could play a big role. Things like how big someone's leg is, muscle tone, how much fat is under the skin, even how deep those muscle spindles actually sit within the muscle tissue. All these could affect how much of that surface stimulation actually penetrates effectively to the target receptors.
So the dose reaching the target might vary a lot.
Could be, and it might also connect back to that stochastic resonance idea. Maybe there's an optimal level of this electrical noise for enhancing sensitivity, and that optimal level is slightly different for everyone. The fixed 90% of skin threshold might have been closer to the spindle optimum for some people than others.
Fascinating stuff. Okay, let's bring this home. What's the big picture significance? The so what? Why should we, care about this?
Well, the really exciting part is that it shows, quite convincingly, that these undetectable signals can directly tweak how our motor system learns and adapts. And it strongly suggests it's happening by influencing proprioception, that deep muscle sense.
And that could have real practical uses down the line.
You can certainly see the potential. Think about rehabilitation, especially for walking gait rehab. People recovering from stroke, spinal cord injury, some neurological conditions, they often struggle precisely because their proprioception is impaired.
They don't have a good sense of where their limbs are.
Exactly. So if you have a tool like this subsensory stimulation, that could potentially modulate how their brain processes proprioceptive signals or how muscles respond to stretch. Well, you might be able to use it to gently guide or enhance their motor relearning during therapy, help them make more targeted changes.
And even though this specific study used subsensory signals, it kind of echoes findings in the broader field of electrical muscle stimulation, or EMS, doesn't it?
It does. The Oriems Fit blog post where we got this simplified summary makes that connection. They point out that EMS technologies, which often use signals you can feel to activate muscles, are already used quite a bit to help with things like movement, balance, coordination, even recovery after hard exercise or injury.
Right.
So this research into subsensory effects, it adds another layer. It suggests electrical signals might influence our motor pathways even without causing obvious muscle contractions or sensations. It reinforces the general principle that electrical inputs can interact with our nervous system in potentially helpful ways.
And Oriems Fit, who run that blog, they focus on wellness tech, including EMS, right? It's an Australian brand, I think.
That's right, Australian owned. Their blog does a nice job of taking complex studies like this and making the core ideas accessible, while still linking you back to the original research paper if you want the full scientific detail. It highlights the kind of science that explores the concepts behind how electrical signals might support the body's movement and recovery systems. And yeah, their focus is on those wellness applications. They've even won awards like Best Product of the Year from productreview.com.au for a couple years running.
Good context. But it's crucial to remember this was fundamental lab research on healthy people.
Absolutely. And that brings us to the limitations we need to keep in mind.
Like the stimulation not being perfectly targeted.
Right. Surface electrodes spread the current. While they aimed for muscle spindles, it's possible other nearby nerves were affected too, even at low intensity. And as we discussed, the actual stimulation reaching the spindles probably varied a lot between individuals.
And that elegant theory about IA and type 2 fibers?
It fits the data beautifully, but it is still a hypothesis. It needs more direct testing, maybe combining the stimulation with EMG to measure muscle activity patterns, or ideally, though much harder, trying to record directly from the relevant nerve fibers.
And definitely the fact that these were healthy young adults.
Huge point. You can't just assume the same thing will happen in someone older or someone with an existing injury or a neurological condition that already affects their proprioception or motor control. We need studies in those populations.
And drawing from the source material, especially the disclaimers you see on sites like the Oriems Fit blog,
Mhm.
this kind of discussion is informational, right?
Essential point. This is fascinating science, but it's not medical advice. Wellness products using electrical stimulation are generally not medical devices, and the people discussing them, like us or on blogs, aren't doctors. Always, always talk to a qualified healthcare professional about health concerns or before trying new treatments or devices. So wrapping it up, what this deep dive really shows is that tiny electrical inputs, things happening below our conscious radar, can subtly but significantly change how our nervous system adapts our movements. And it seems to work by tweaking our internal sense of body position.
It's kind of mind-bending, isn't it? How adaptable our system is and how these different layers of input might be influencing us all the time. Makes you wonder about leveraging these subtle signals more intentionally.
And maybe leaves you with this thought. If undetectable electrical signals can influence something as complex as learning to adjust your walk, what other really subtle sensory cues, maybe tiny variations in pressure under your feet, or faint internal feelings might be constantly shaping how you perceive the world and control your body in ways you don't even realize?
Definitely food for thought. If you want to dig into that simplified breakdown of the Harvard and UCD study we discussed, check out the Oriems Fit Research Digest blog. They lay it out clearly and link to the original iScience paper too. Remember, Oriems Fit is that Australian-owned brand working in wellness technology.
Thanks for joining us on this deep dive.
Hope you walk away maybe adapting slightly differently, feeling informed and curious.